So this video is going to talk about how to get to another star, or whether we can possibly get to another star. The short answer is no, we can't get to another star because it's really, really, really far away. So let's go through the math of why we can't actually get to another star. So the closest star is Alpha Centauri, which is about 4.2 light years away, which is sort of a long ways away. Let's just do some simple thing first, the most naive thing that we possibly can, which is like, hey, we want to get into a spaceship and we want to accelerate up to some significant portion of the speed of light. Let's say that we want to go about half the speed of light. A good acceleration that we humans seem to really like is about 1 g, because we live on Earth and we want to be able to pretend that we're on Earth. So if we could get into a spaceship and accelerate at about 1 g, that would be really nice for us. So how long would it take to get up to half the speed of light if we accelerated at 1 g continuously? We have the velocity is equal to the acceleration times delta time. So we want to solve for the amount of time because we know the velocity is going to be about half c, and then the acceleration that we want is about 10 meters per second. So the delta t for that is 1.5 times 10 to the 7th seconds, which seems like a lot of seconds, but then you divide it by 86,400 seconds per day, and you get that it takes about 174 days, which is roughly half a year. So that's actually not that bad. So how far do we go in 174 days if we do a constant acceleration? Well, so we use the formula x equals 1/2 at squared, and then we get that the distance is about 1 times 10 to the 15th meters, which seems like a very, very long ways. We actually didn't ever say what is a light year, so let's actually do that calculation. X is equal to velocity times delta t, so velocity is c. If we want to determine what a light year is, it's basically the distance that we would go in 1 year traveling at the speed of light, which if you do that math, it is 9 times 10 to the 15th meters. During our acceleration phase, we went about 1 times 10 to the 15th meters, which is roughly 0.12 light years. So during the time when we're accelerating from 0 to half the speed of light, we go about 0.12 light years, which is not too far. If we accelerate up to half the speed of light, we go about 0.12 light years, and then when we decelerate, when we get there, we go about 0.12 light years. So that total is about 0.24 light years, about a quarter of a light year. And it will take about 1 year to do that acceleration and deceleration phase. We have 4.22 light years to go. We go about 0.24 light years during the acceleration and deceleration phase, and we have roughly 4 light years that we have to travel during the cruise phase of this trip. Since we're going half the speed of light and we are going 4 light years away, the math is really easy. It'll take 8 years to get there. So the travel time to get there is a half a year to accelerate, 8 years to cruise, and then a half year to decelerate. So a total of 9 years. That is not very long at all. But there is a problem with that. The big problem is that we can't accelerate in space at 10 meters per second for very long at all. Accelerating at 10 meters per second squared for half a year is 100% unrealistic. And in fact, we can only do it for about 10 minutes in space. The rocket just has to be so astronomically big that we just can't do that. So 10 minutes, 20 minutes at the most is about what we can do. So that's somewhat sad. So let's go up to here, and the issue comes in the form of the rocket equation. So the rocket equation basically describes how much change in velocity you can actually get from a rocket. The problem with a rocket is that in order to start accelerating, you need to bring all of the fuel with you. And so you have to start off with a gigantic rocket. And in order to accelerate at like 10 meters per second squared, you're going to have to spit out a gigantic amount of fuel, which means that you're going to need even more fuel. It just becomes untenable. Your rocket becomes so big that you just can't build a rocket big enough. This equation actually describes this as an exponentially increasing size of a rocket. So the change in velocity is equal to the exhaust velocity, which is basically how fast particles come out of your exhaust nozzle. And then you take the natural log of the ratio in the masses before the rocket and after the rocket. And actually you have the mass of the rocket including the fuel, so the mass at the very start of your burn divided by the mass at the end of the burn. So basically the full rocket divided by the empty rocket. And so you're taking a ratio of basically how much fuel you have to use compared to the rocket size. All right, and that tells you how much delta V you can actually get from your rocket with this equation. We can reorder this equation here to figure out how much fuel you would need to have some particular delta V. So when you do that, you get the delta V is equal to natural log of MO over ME, where MO is the mass of the empty rocket and MF is the mass of the fuel. You basically go through this math down here, and you get the mass of the fuel is equal to the mass of the empty rocket times e to the delta V over V exhaust minus 1. All right, so let's actually do an aside. Let's use the rocket equation to figure out how much fuel it takes to get to orbit. So to get to orbit, our delta V is roughly 8,500 meters per second, because we have to go both up and we have to go horizontally. We have to get up to about 7,600 meters per second to go into low Earth orbit, but we need a couple thousand meters per second to actually get up to about 500 kilometers. And so the delta V total that you need is roughly 8,500 meters per second. The exhaust velocity of a modern rocket is about 3,000 meters per second. Say the payload mass is about 10,000 kilograms, and say the rocket is roughly 30,000 kilograms. That's actually a pretty light rocket, but whatever. The empty rocket then is going to be about 40,000 kilograms. That's basically the size of the rocket plus the payload. And so let's figure out how much fuel you need. So the mass of the fuel is equal to the empty mass times e to the delta V over V exhaust minus 1. You put in those numbers, you solve for everything, and you get the mass of the fuel is roughly 640,000 kilograms to lift about 10,000 kilograms into orbit. That's a lot of fuel. That is a lot of fuel. This number here, this 16, is roughly like a multiplier of like how much fuel does it take for every kilogram of payload to get up to orbit. You need roughly 16 kilograms of fuel to get you up to get 1 kilogram up to orbit. All right, so let's look at interstellar travel. So for interstellar travel, we're going to assume the delta V that we want is half the speed of light, which is 1.5 times 10 to the 8th meters per second. Our exhaust velocity. Well, we talked about exhaust velocity over here. That's 3,000 meters per second. And that is like normal, everyday fuel. But let's say that we actually have some advanced fuel here, and we're actually using 30,000 meters per second, so like 10 times the efficiency of the fuel. And that's really like an electric propulsion. And that technology is coming online. It's slowly coming online. We can't power like big satellites or big ships or anything like that right now, but we have used that for smaller satellites, this electric propulsion. Yeah, that's about the most advanced fuel available today. So if we look at how much fuel it requires, we look at the empty mass, e to the 1.5 times 10 to the 8th divided by 30,000. So that is e to the 500th power. If you do that in a normal calculator, it will just give you an error. But on my phone, it actually gave me a real answer. So e to the 500th is 10 to the 217th. Which is a lot. That is a lot. So the amount of mass in the universe is roughly 10 to the 80th. So 10 to the 80th is the amount of mass. Actually, this is the number of particles in the universe. And so that's more mass by, several orders of magnitude than is in the universe. The short story is you can't accelerate up to half the speed of light using a conventional rocket. You can't get up to anywhere close to the speed of light by using a rocket like we use to get off of the Earth or to the moon or to Mars or anything like that. We have to develop brand new technologies to actually do this. They don't exist yet. We just can't do this. Yeah, that's basically the short answer is those technologies just don't exist. So the question then is, how fast could we actually go? Like if we used technology that exists today, what is the fastest that we could actually go? Go back to the rocket equation. Delta V is equal to the exhaust velocity times the natural log of me plus mf over me. So let's assume that our mass of the fuel is roughly 100 times the mass of the empty rocket. 99% of our rocket is fuel, while we have 1% as payload. That is a really, really, really big rocket. Or it's a very small, very, very tiny payload, but it's still a big rocket. Pretend we can use 30,000 meters per second. So like we're building a rocket that can use electric propulsion, and the entire rocket can actually use electric propulsion. That technology doesn't exist yet, but I think it will exist within the next 20, 30 years. So our delta V then is equal to 30,000 times the natural log of 1 plus 100 divided by 1, which is 30,000 times the natural log of 101, which natural log of 101 is about 4.6. And that gives us a delta V of 104,000 meters per second. 104,000 meters per second. That is much larger than anything we have ever built to date. The fastest we've ever gone is around 22,000 meters per second. So this is roughly 6 times faster than anything we've ever built before. This is not using any planetary assists or anything like that at all. This is like technology that is 20, 30 years away maybe. We build a rocket that can go 100 or make a payload go 138,000 meters per second. And so what does that get us? Well, so velocity is equal to delta x divided by time. The time is delta x divided by the velocity. This is 1 light year. And this is the number of light years that it is to Alpha Centauri, 4.22 light years. And this is the number of meters per light year. This is our velocity down here, 138,000 meters per second. And that gives us an answer of 2.8 times 10 to the 11th seconds. And what does that mean? Well, so you divide that by 86,400 to be the number of seconds per day, and you get that it will be 3 million days, which still is, I don't know what that means. So you divide by the number of days per year, and you get that it will take 9,000 years. So The answer to can we get to another star is in 20 to 30 years, we will be able to build a rocket ship that will get us to another star in about 9,000 years. And if we want to get there much faster than that, that technology just doesn't exist yet, and we're going to have to do a lot of research. So I hope you enjoyed this problem. It is not the answer that we want, but it is the answer we have. So you all should become, jet fuel engineers or really rocket propulsion engineers and figure out new technologies that will allow us to get to another star, before the century is over, maybe. All right. Thank you very much. Bye.